In this example, what we're going to be talking about is we're going to be talking about the Compton effect. And for the Compton effect, what you have is you have this electron, call this an electron, and what happens is irradiated on the electron is going to be some sort of light. Now let's say that we have a reference point here as such, all right? And what happens is that when this electron, which is at rest, it's not moving, when it gets hit with this light, what happens is that the electron gets recoiled in some direction. And the photon, or the light, gets scattered. So this is scattered light. Now there's going to be an angle in which that scattered light is going to scatter relative to some axis. Now we can find this angle in which it's scattered by using the following equation. We can say that lambda prime minus lambda is equal to h, which is Planck's constant, divided by the mass of an electron divided by the speed of light, times 1 minus cosine of this angle. All right? So we want to find the angle for the scattered light. And so the problem reads as such. In a Compton scattering experiment, the incident X-ray have a wavelength of 0.2685 nanometers, and the scattered wavelength is going to be 0.2703 nanometers. Through what angle are the X-rays scattered? Now, the interesting thing about the Compton effect or Compton scattering effect is that you can now treat the photon as though it were a particle as opposed to just being a wave. So let's plug these values in, let's solve this. So this becomes 1 minus cosine theta is equal to lambda prime minus lambda times mass of the electron times the speed of light divided by Planck's constant. Now, lambda prime minus lambda is equal to 0.2703 nanometers minus 0.2685 nanometers, and that is equal to 1.8 times 10 to the negative 3 nanometers, which is equal to, I'm going to convert this into meters, 1.8 times 10 to the negative 12th of a meter. Therefore, we have 1 minus cosine theta is equal to, we can now put in our change in wavelength, which is 1.8 times 10 to the negative 12 meter times the mass of an electron, which is 9.109 times 10 to the negative 31st kilogram times the speed of light, which is 3 times 10 to the 8th meter per second, or meters per second, divided by Planck's constant, which is 6.626 times 10 to the negative 34 joule second. All right, joule second. All these units are going to cancel out. Simply remember the joule is going to be a kilogram meter squared per second squared. So kilogram will cancel, the meters will cancel, and then the here you have a second type, so that'll be per second will cancel with the per second. So you end up getting a unitless number here. And this will be equal to, so 1 minus cosine theta is equal to 0.746 4, 2. All right. Now, we subtract the 1 over here. All right. So what we have is we have a minus cosine theta is equal to a negative 0.2576 is what it when you carry out all the digits. That will become positive. That will become positive. You take the inverse cosine, and you come up with a theta equal to 75.1 degrees. So what this tells us is that this theta, the angle here, the scattering angle, is going to be 75.1 degrees. And what this does, or what this shows, is that you can treat light as a particle, because it's actually going to, because it doesn't really make sense for a wave to get scattered. However, it does make sense for a particle to get scattered. And it really doesn't make sense for an electron to move unless it, you think of something in terms of, for instance, collisions. All right. If you have any other questions about the Compton effect or anything else in this chapter, please let me know.